In this particular module, we will be discussing fundamentals of probability and statistics. Nowadays, probability and statistics plays a very important role in all walks of life, all engineering and science disciplines, in social sciences. In fact, we can say that there is no area of human activity where probability or statistics is not used. The subject of probability is as old as the civilization itself. However, the modern theory of probability as we know today has its roots in games of chance, and particularly in 15th and 16th century Europe, when the gambling games were being played in casinos, roulette wheels, in the form of dice games, card games, etc. Then some of the people got interested in knowing the that what are the chances that if they bet on a certain event, then whether it will be more likely or less likely. For example, in a game of cards, they would like to know whether a particular player will get all the 4 aces or all the 4 kings, or whether he will get the top 4 cards of a particular denomination. This led to the certain correspondence and activity among the mathematicians, especially two of the. So, today we will discuss basically the laws of probability, the basic laws of probability. Some of the famous mathematicians of the day, for example, Fermat, Pascal, they had a famous correspondence in which they discussed the elementary laws of probability. However, the first published work is probably by Huygens in in the year 1657 in his book. There is also contribution by James Bernoulli around the same time. The landmark, or you can say the first milestone in the development of the subject probability, can be considered by the monumental work by Laplace, the French mathematician, in his book Théorie analytique des probabilities. Laplace covered all the development of the subject of probability which was known till that day. To that he added his own theories, and this gave a firm foundation and a mathematical treatment to the subject probability. Some of the famous contributions to the subject of probability are by von Mises, Probability, Statistics and Truth. The modern probability theory, that is after the Hilbert's development of that any mathematical theory should have an axiomatic setup, and from there the entire theory should be able to derive. This led to the axiomatic development of the probability theory, and A. N. Kolmogorov, the Russian mathematician, published a book in 1933, Foundations on the Theory of Probability. Let us see that what are the fundamental units that one should know, or the fundamental definitions for the development of the subject of probability. So, when we give a typical statement that it is likely that it will rain today, or I may miss my train today, or my for example, if I am doing a study, I may say that my study is likely to be successful or unsuccessful. These type of statements are in a sense giving us a measurement of how much likely an event is, but in the first place we may not actually give a number, we may just say that okay, it is likely that it will rain today without quantifying it. However, if we say that there is a 75% chance that it will rain today, then we are putting measurements with that. So, the subject of probability is related to giving numerical values to the probabilities of various statements, and therefore, it deals with certain phenomena where things are uncertain. For example, let us look at two types of experiments. One experiment is that we take two molecules of say hydrogen and a molecule of oxygen and we mix them. We know that the reaction of it would lead to the water. Now, this is an experiment in chemistry, and similarly there are various experiments in science and engineering, where we carry out an experiment under certain conditions and we come up with a certain conclusion. We know that this will be the outcome of the experiment. Such experiments are known as deterministic experiments. So, fundamental unit you can say in the study of the subject probability and statistics is an experiment. So, an experiment can be a deterministic experiment, I gave the example of a deterministic experiment just now. Another experiment could be where if we conduct the experiment, we are not sure of what outcome will be there. For example, if we toss a coin, then we may get a head or tail, or we may also include the possibility that it may stand on its sides. If we toss a die, then we may get any face up, for example, 1, 2, 3, 4, 5, 6. If we talk about the weather tomorrow, then the weather could be sunny, it could be cloudy, it could be rainy, there could be thunderstorm. If we are talking about say next 10 years, say status of the number of earthquakes in a particular seismic zone, then there may be one earthquake, there may be no earthquake, there may be 3 earthquakes, or there may be 15 earthquakes, and so on. Now, these are the kind of events where we are unable to know the outcome of the experiment beforehand. Now, we say experiment does not mean that only laboratory experiment. Experiment means observing or conducting something under certain conditions. So, when we say weather, then we are only observing the weather, because as we know that there will be spring, there will be summer, then there will be rainy season, then there will be winter, and so on. So, the weathers happen due to certain natural phenomena. However, when we want to observe that, then it is considered as an experiment, and if we are looking at say day to day or behavior over a period of time, then it is a random experiment. A non-deterministic experiment is known as a random experiment, because we are not sure of what outcomes will be there in the beginning. So, random experiments are the one here, the outcome is not certain beforehand. Now, one may just question that if we are not knowing the outcome beforehand, then why do we actually study the subject of probability? For example, if we are looking at the tossing of a coin, then certainly it can be head or tail, but it is not known at each toss of coin whether we will get a head or tail. But there is another feature of such experiments which allows us to study the subject of probability on a more theoretical basis. For example, if we conduct the experiment say 100 times, suppose the coin is a fair coin, we may observe something like say 48 heads and say 52 tails out of 100 times. Suppose we conduct the experiment of tossing of a coin 1000 times, we may observe that there are say 505 heads and say 495 tails. That means, if we are conducting it a large number of times, we may observe a pattern, and that pattern gives us the probability of individual events. For example, we may safely say that the probability of occurrence of a head is half year, or the probability of the occurrence of tail is half year. Similarly, if it would have occurred that my conducting of these experiments would have yielded, for example, in the toss of 100 times, suppose we have 60 heads and say 40 tails. Similarly, suppose in 1000 we may get something like say 602 heads and say 398 tails. Then we may be more inclined to say that it is a biased coin in the favor of head, and we may put say probability of head as say 2 by 5, sorry 3 by 5, and probability of tail as 2 by 5. Therefore, what we observe here is that individual experimental outcomes are not known, but there is a long term statistical regularity. This term is known as statistical regularity, that is the long term behavior that one can say. So, for example, in a 1000 births in a city hospital in a period of say 6 months, we may expect that there are 500 girl childs and 500 boy childs born. If we observe the weather pattern over several years in a monsoon region, then we may say that during the monsoon the amount of rainfall may be say 100 centimeters. Or if we are observing the weather pattern of drought and rains, we may say that after every 10 years there is a likelihood of a drought year. So, for example, we may say that the probability of a drought is 1 by 10. So, this long term behavior that we can make about, that we can predict about a uncertain event justifies the study of the subject probability. Now, we introduce the examples of random experiments. So, we may consider various kinds of phenomena. For example, I just mentioned about say tossing of a coin, throwing of a die, picking up a card from a deck of cards, etc. However, these are not the only textbook kind of examples that are random experiments. There can be many more. For example, we may observing the number of vehicles crossing at a busy traffic signal during an hour. So, here for example, the number of the vehicles could be 0, 1, 2 and so on. The amount of rainfall in a certain say geographical region during a year. So, depends upon the region. Suppose the region is such that it receives lot of rain, then this amount could vary from say 20 centimeter onwards to say 200 centimeter. You may have interval like this. The weight of a child is recorded at the birth. So, different children will have different weight at birth. So, they may vary from a few 100 grams to few kilograms kind of thing. The number of times a child contacts a cold infection during a year, the number of students scoring more than qualifying marks in an examination. So, for example, the total marks are 100 and the qualifying marks are fixed as say 60. Therefore, how many students out of the total number of students which are appearing, how many of them will cross that qualifying marks, that will become a random experiment. You are going on a road and you arrive at a traffic signal. So, the traffic signal may be green. So, you may just cross, or it may be red, and in that case you may have to wait dependent upon the total duration of the signal. For example, it may vary from 0 to 3 minutes. So, the waiting time at a traffic signal. So, suppose we are recording in seconds, then it could be from 0 to 180 seconds, the maximum limit till which the signal may be having a particular sign. The time to decay of a page in a textbook. So, this could be the time recorded in years. For example, it may take say 20 years to 100 years for the pages to decay, or maybe 20 years to 200 years for the page to decay. The time for onset of a disease since the infection. So, for example, one is infected with say HIV virus, and then the time when the AIDS disease develops in the person. So, that is a random experiment. The total food grain produced during a harvesting season. The number of units of an item sold from a store during a day. So, you can see that the examples of random phenomena as varied as possible, and the examples are ranging from engineering, physics, medical, social sciences, economics. So, almost there is no area of human activity where the random phenomena is not there. In fact, the quantum mechanics assumes that the movement of the electrons is random, and that is why the modern theory of physics, or as it is called statistical physics, is there. Now, we look at some basic terminology which is used in the subject of probability, and then we will define the probability. So, let me take the basic unit of a random experiment is a sample space. So, a sample space is the set of all possible outcomes of a random experiment. So, the usual notations one can use S, omega, theta, etcetera. So, let me look at the examples that we discussed just now. So, for example, if we are looking at the number of vehicles crossing at a busy traffic signal during an hour, then here the sample space we may write as the numbers 0, 1, 2 and so on. If we are looking at the amount of a rainfall in a certain geographical region during a year, and as I mentioned that the area is such that it receives lot of rain, then my sample space can be expressed as say an interval 20 to 200, where the unit of measurement is in centimeters. The weight of a child at birth, so it may be as small as a few hundred grams to say 500 grams to say 5000 grams. It may vary little more also depending upon what feature we are studying here. The number of times a child contacts cold infection during a year, once again the number could be 1, 2 and so on, and it may end up at a finite, because the total number of days in a year is 365. So, certainly the number cannot be very large. You may put say 0, 1 to 50. The number of students scoring more than qualifying marks in an examination. So, suppose the total number of students are n which are taking the exam, then the sample space could be the waiting time at a traffic signal in seconds, for example, it could be 0 to 180, the time for decay. So, in any experiment one may define what is the sample space dependent upon what is our area of interest. Then what is an event? Any subset of the sample space is called an event, and we usually employ English letters in capitals to denote the events. So, for example, if we look at the number of vehicles crossing at a busy traffic signal, I may define the event A as the number of vehicles is less than 10. Then naturally, A is consisting of 0, 1 to 10. This is a subset of S. I may consider say the number of times a child contacts cold. So, we may say the number of times the child contacts the cold. So, we may put is say more than 3. In that case, the set B will be 3, 4 and so on. Suppose we are putting the upper bound as 50. So, this is a subset of, here if I denote it by say omega, then this is a subset of omega. So, event is a subset of the sample space. However, we may have extreme cases. When we say subset, then empty set is also a subset, the full set is also a subset. So, if we say full set, so S is a subset. So, this is called sure event, and phi is a subset of S, this is known as impossible event. For example, if we say that the weight of a child at birth is minus 32, then it is a impossible event. Suppose we say that the number of vehicles crossing at a busy traffic crossing is say 1 million, then this will be impossible event, because it cannot cross the total number of vehicles which are available there and so on. Now, when we associate sets with the events, then there are set operations like union, intersection, complementation, etc. So, in terms of events they have various interpretations. I would like to explain this now. So, we may consider say A union B. Now, if there are two events A and B, A union B represents occurrence of either A or B or both. Now, we can generalize this notation. For example, if I have A 1 union A 2 union A n, then we may say this is occurrence of at least one A I for I is equal to 1 to n. We may even talk about an infinite union I is equal to 1 to infinity. The interpretation of this will also be the same, occurrence of at least one A I, occurrence of at least one A I. Now, here I will be 1, 2 and so on. Similarly, if we consider the concept of intersection of sets, then here intersection of the sets will denote the common elements belonging to A and B. So, this means that both A and B occur. So, this we can say simultaneous occurrence of events A and B. Now, this concept can further be generalized to n events or infinite number of events also. So, this is simultaneous occurrence of AIs, that is all AIs occur together. Then there is a concept of complementation. For an event A complement denotes not happening or no occurrence of A. Similarly, we may interpret A minus B. A minus B in the set theory denotes the set of elements which are in A, but not in B. So, this will become A intersection B complement. That means, occurrence of A and not occurrence of B. Then there is a concept of, because when we consider the concept of intersection, the intersection could be phi also. If the intersection is phi, if A intersection B is phi, then they are known as disjoint sets. So, here we call them mutually exclusive events. The meaning is that if A occurs, B cannot occur, and if B occurs, then A cannot occur. So, this is events A and B are said to be mutually exclusive events. That is, occurrence of one excludes the possibility of occurrence of the other. There is also a chance that some of the events, for example, A union B is equal to the full sample space. If A union B is equal to omega, then all the possibilities of the sample space are considered by A and B. Then we say A and B are exhaustive events. This can be generalized. We may have I is equal to 1 to n is equal to omega, or we may say union I is equal to 1 to infinity is equal to omega. See, for example, if we are considering tossing of a die, if we are tossing of a die and we consider A I as I, then A 1, A 2, A 6, they will exhaust all the possibilities of 1 to 6. So, they are exhaustive. If we are looking at say weather on a day, and we define the event say E as sunny, F as say cloudy and G as say rainy, then all the possibilities of the weather are exhausted and we may say E, F, G are exhaustive. Now, we are ready to look at the one of the preliminary definitions of probability, which we call as a classical definition of probability. This can be attributed to Laplace. He was the first one who gave it in this particular form. Let a random experiment be conducted. Suppose it has n possible outcomes and these outcomes are exhaustive. That means, we have considered all the possibilities, equally likely. Equally likely means that each of them has the same chance of appearing and mutually exclusive. That means, occurrence of one will be excluding the possibility of the occurrence of the other. Let E be an event for which m of these outcomes can be considered to be favorable. Then the probability of E is defined as probability of E is equal to m by n. So, the definition is, as you can see, it is applicable to the experiments where we have a finite number of outcomes, all of which we can enumerate, and we are putting additional restrictions such that they are exhaustive, they are mutually exclusive and also they are equally likely. In those cases, this definition can be applied. Let us look at some very simple example, say tossing of a fair die. Your sample space consists of 6 possibilities and we associate say event A by saying the number is even. Now, if we want to find out the probability of A, then there are 3 favorable cases 2, 4 and 6, total number of possibilities is 6. So, you get half. Suppose we say the number is less than 5, then number is less than 5 has 4 possibilities here. So, probability of B will be equal to 4 by 6, that is equal to 2 by 3. Suppose we consider say tossing of 2 fair dice and we say E is the event that the sum is say 7. Then what are the possibilities here? When we toss 2 fair dice, the total number of possibilities is 36, 1 1 1 2 2 1 2 2 up to 2 6 3 1 3 2 3 6 and so on. There will be total 36 possibilities, and if we assume that the dice are fair, then each of them will be. So, the set E will be represented by 1 6 2 5 3 4 4 3 5 2 and 6 1. These are the 6 possibilities which will lead me the sum 7. So, probability of E will become equal to 6 by 36, that is equal to 1 by 6. Suppose we take another example here. Four players A, B, C, D are distributed 13 cards each at random from a complete deck of 52 cards. What is the probability that the player C has all 4 jacks? Now, here you look at this problem, the total number of possibilities for each player. So, there are 4 players and they are distributed 13 cards each. So, the total number of possibilities for a player C, because we are interested in the event for the player C, the total number of cards that the player C gets is 13 out of 52. So, if we consider the possibilities, it will be 52 C 13. Now, he is getting all the 4 jacks. That means, out of his 13 cards, he is now total there are 52 cards, out of which there are 4 jacks, and he gets all the 4. So, 4 C 4, and from the remaining 48 cards he gets any 9 cards. So, this will be the probability of player C has all 4 jacks. So, this answer comes by direct counting, assuming that all the cards are equally likely to be distributed to all the players. This definition is helpful for answering questions of this nature, where the sample space are finite and we are having the facility of observing, or you can say enumerating, being able to enumerate all the possibilities. However, this has some practical difficulties. For example, we may have this total number n need not be finite or determined. We may not even be able to determine what is n. Another thing is that we are assuming here that the events are, or the outcomes are equally likely. The meaning of equally likely, which I mentioned, is that they have the same chance of occurrence. Now, chance is associated with the term probability. We are defining probability here. In that sense, this definition is circular. The definition fails. We are already assuming that each outcome has equal probability. Therefore, this particular type of definition is applicable only to theoretical kind of exercises. The definition of probability here uses the term equally likely, meaning outcomes which have the same probability of occurring. Thus, the definition is circular in nature. A more practical definition was developed, and this is based on the empirical evidence. When we make usual statements, it is likely that it may rain today. For example, if we have observed 3 days of intense heat and humidity in a region, then we say that on the 4th day evening, we may say in the morning, we say today evening it may rain. Now, this is based on our experience. Similarly, when we are observing the performance of students and we make a statement, we fix up the qualifying marks as 60, and then we say that nearly 50% of the students will qualify. Now, this is based on our previous experience or previous experimentation for the same event. As I already mentioned that the subject probability itself is of interest because of the feature of statistical regularity or long term prediction. Therefore, another definition which is a more statistical definition is based on the empirical observations. So, we give empirical definition of probability. This is also called relative frequency definition, relative frequency definition. Now, we are looking at the outcomes of a random experiment. Based on that, certain event is there for which we are looking at the probability. So, for example, whether it will rain after 3 days of intense heat, etcetera. What is the probability of the students qualifying a given examination? What is the probability of a patient recovering from a certain disease if he is given a certain medication? So, in all these cases, we are observing. So, for example, patients are being given certain medicine for certain disease, and then we have the data that how many of them may be recovering. So, maybe 90% are recovering, maybe 80% are recovering, and so on. Now, each unit of observation. So, for example, one patient is being given the medicine or medication for a certain disease, then second patient is given, and this we are observing over a period of time. This is considered as repeatedly conducting the experiment, and we may say roughly that it is conducted under identical conditions. So, and also we may assume that occurrence or happening of one experiment, that means, whatever be the outcome of one experiment does not affect the outcome of the next time repetition. So, for example, one patient is given a certain medicine, he may recover from there, and now a second patient comes with the same disease and the same medication is given, he may not recover. That means, effect of one occurrence should not be there on the other one. So, we say that the random experiment is repeated under identical conditions and also independently. Now, we see how many times over a period of time or how many times over a certain number of trials this particular event occurs. Now, this ratio is some value, and over the long range when we are observing over a period of time, this will stabilize. This is known as the probability of that event. So, let me write it here. Consider a random experiment and it is repeatedly conducted under identical conditions and the repeated trials are performed independently. Let say P n be the number of occurrences of a particular event A in n such repeated trials of the random experiment. Then we define the probability of the event A as limit P n by n as n tends to infinity. That means, over the long term, what is the ratio of occurrence of the event in which we are interested to the total number of trials of the experiment. Let me explain through an example here. Consider, say, let us consider weather report of a region for say 1000 randomly selected days from say 30 years data. Suppose the weather pattern is say sunny day, cloudy day, rainy day, sunny day, cloudy day, rainy day, and so on. The pattern is somewhat fixed, that is 2 sunny days followed by a cloudy day and then a rainy day. Now, we are interested in finding out the probability of, we want the probability of a sunny day. So, we look at this ratio P n by n. Now, this P n by n, when the first trial was there, we observed sunny day. So, the ratio becomes 1 by 1. In the 2 trials, 2 days it was sunny, 2 by 2. Now, the third day turned out to be cloudy. So, the number of sunny days in the 3 trials is also 2. The next day turned out to be rainy. So, the number of occurrences of the event S was 2 out of 4 also. Then 3 by 5, 4 by 6, 4 by 7, 4 by 8, 5 by 9, 6 by 10, 6 by 11, 6 by 12, and so on. Now, we want to find out the limit of this. If we just observe like this, it is difficult to find out the limit, because the numbers are changing rapidly. So, we put it in a more mathematical form. We can write like this. It is equal to, if we observe each 4th occurrence here, this is of the form 2 by 4, 4 by 8, 6 by 12, and so on. That means, we can write it as 2 k by 4 k whenever n is of the form 4 k. If we observe here, it is 2 k by 4 k minus 1, that is whenever n is of the form 4 k minus 1. Here it is equal to 2 k by 4 k minus 2, whenever n is of the form 4 k minus 2. It is of the form 2 k minus 1 by 4 k minus 3, whenever n is of the form 4 k minus 3, for k is equal to 1, 2, and so on. clearly you can see here that each of this subsequence converges to half. This is equal to half, as k tends to infinity this goes to half, as k tends to infinity this goes to half, as k tends to infinity this goes to half. So, clearly you can say limit of p n by n as n tends to infinity is equal to half. So, probability of a sunny day is equal to half. So, this is a experimental you can say demonstration of this method of the relative frequency. So, here if you see that 2 sunny days followed by 2 non sunny days, if that is the pattern, then definitely the probability of a sunny day over a period of time should be half. So, relative frequency definition is based on the experience, and this is the most widely applicable definition of the probability today. The definition which I gave earlier as a mathematical definition is more applicable for theoretical problems, where we can see that the conditions of the are satisfied. Now, in this also there may be some discrepancies. For example, we are taking the ratio. Now, that ratio will have a limit. Now, that limit could be 0 or 1 also. For example, you may say p n is equal to say n to the power 1 by 3. Now, n to the power 1 by 3 is not a negligible number, but if I consider p n by n, then that will become 1 by n to the power 2 by 3. So, that will goes to 0. So, probability of a non null event may be 0, which looks little counterintuitive, although in the long run it has a meaning. What it means that as n becomes large, n to the power 1 by 3 becomes much smaller compared to n. Similarly, we may have say p n is equal to n minus root n. In that case, p n by n that will converge to 1. Now, here you can see that the event is not a sure event. So, probability of a non sure event may be 1, which is again little counterintuitive, although from the statistical description of the probability this is all right, because what it says that if we have n large, then out of that the number of occurrences of the event is almost full. That means, sometimes it may not occur, but that number is negligible. However, because of these drawbacks, we cannot use these definitions as the you can say axiomatic definitions, because they do not satisfy all the conditions. There are certain other problems also. For example, this requires that the experiment be performed, or we should be able to observe the occurrences and the outcomes of the occurrences. Now, there can be various experiments where this is not possible. For example, rare phenomena, or suppose we are looking at industrial experiment, and an industrial experiment, suppose it is a large scale industrial experiment. In that case, if we have to look at whether the system will fail, at what time it will fail, then certainly we have to wait till the time when the system actually fails. So, in many of these conditions, the direct application of the definition is not possible. Based on this, in Kolmogorov, the Russian mathematician, gave a now the well known axiomatic definition of probability. So, we have the sample space and we consider a class of subsets of omega. That means, these are events. Now, this should satisfying the following two conditions. One, that for every E belonging to omega, E complement also belongs to omega. That means, it is closed under the complementation. And second is that for any sets A 1, A 2 and so on belonging to B, union of A I also belongs to B. That means, it is under closed under the infinite unions also. Such a B is actually called, this is called a sigma field or sigma algebra. This is a algebraic structure. However, we are not getting into this. The main purpose is that when we are considering a random experiment and its outcomes, then all the relevant events should be included in the subject under study. That means, whatever set we are considering, it should include all the relevant events, and that is why we make it closed under the operation of complementation and the infinite unions. As we know that this will further allow infinite intersections, it will allow the differences. That means, all the possible set theoretic manipulations will be included in the relevant space, and therefore, we will be able to conduct the study of the probability. That means, we can find out the probabilities of the related events, provided a certain probabilities are known to us in advance, either by the first definition, that is the classical definition, or by the second relative frequency definition. That means, probability of certain events may be known to us, and thereafter we can use them to derive the probabilities of various other events. So, in the following class, I will be discussing the axiomatic definition of the probability, its ramifications, and then various important results of probability.